So I hope that went okay. Make sure you try those before you just watch me do them, because it's kind of like a mini test. Okay, so today we're going to talk about springs, and springs have to do with Hooke's laws. So springs exert forces on objects. The amount of force exerted by a spring depends on two things. It depends on the type of spring used. So if you have suspension for a car, it's very different than the spring inside of a pen. And it also depends on the distance you stretch or compress the spring. So this is our formula for finding spring force. So Fs is spring exerted by force exerted by a spring. So K is spring constant, which every spring has. The bigger the spring constant, the more rigid the spring is. So spring constant is kind of like coefficient of friction. This is the value given to springs. And then X is the distance or displacement from the equilibrium position. So how far the spring is stretched from its equilibrium position. So why is that negative in the formula? So you'll notice that Hooke's law has a negative sign. And the reason for this is because the restoring force is always opposite the direction of the displacement. So we can draw on a spring here. So here's my spring, and here's my spring stretched out. Okay, so when I stretch it out, right, this is how far I stretch it out. This is my displacement, is this way here. But think about a stretched out spring. It always wants to go back to the original position. So my spring force is in that direction, because the spring will always try to, if this is what the spring looks like in equilibrium position, the spring is always going to try to go back to that equilibrium position. So the displacement and the spring force are in opposite directions. So that's why that negative is there. But we know that. We can draw a free body diagram. That's not tricky. So when I'm doing this, I get rid of that negative. I think that's negative is stupid. So I just say Fs is equal to Kx, and I know my directions. Yeah, so don't even put the negative in there. And then we have another formula, which is spring potential energy, where EPS is spring potential energy, K is spring constant, and X is the distance or displacement from the equilibrium position. Okay, so what makes this tricky is these two formulas look very similar, but one of them is spring force and one of them is spring energy, and that's where you can find them on your data booklet as well. So if you want to find the first one, the spring force, you find that under this forces and fields category. So there's Fs equals Kx. If you want to find spring potential energy, then you're going to be using this one down here, right? So they're in different spots and they're for different things. Forces in newtons, energies in joules. Yeah, don't mix them up. So we can also graph Hooke's law. So lots of times the amount of force changes as like the spring gets harder and harder to compress or stretch out the more that you do it. So we can do it in graph form as well if that's changing. So remember that slope is equal to change in y over change in x, right? So if we take a look, what we're doing is we're taking y, which is force, and we're dividing it by our extension or distance like that. So I don't know if we've seen a formula like that. And we can also take a look at our units here. So it's a Newton per meter would be our units. This is newtons, this is meters. And if we go back, right? Oh, look at this. This is a Newton per meter. That could be helpful. So that tells us that slope must be, oh, it's our spring constant. Right? So what is the area under the graph equal? So we could find this area under here. So if we found that area, it would be area is equal to y times x. So it'd be force times distance, and ooh, force times distance, I recognize that. Force times distance equals work. So this is area under the graph is equal to work, or remember that work is equal to change in energy. So if we're talking about a spring, it could be our change in spring potential energy as well. So those are the two parts of the graph that you need to know about. Okay, so let's do some questions here. So a spring has a constant of 43 newtons per meter and a mass of 300 grams suspended to it. The spring is attached to the ceiling. Draw a free body diagram for the stationary spring and determine the extension of the spring. Okay. So here's our free body diagram. Here's our mass right here, and it's 300 grams, so 0.3 kilograms. So we can draw a free body diagram. So gravity is acting on this spring, but there's also a spring force. It's trying to go back to that initial position, so there's a spring force up. And it says in the question that it's stationary, and we know if it's stationary that these two are going to equal each other. And we know spring force with our new formula is equal to Kx, and Fg is equal to mg. So we're trying to find out how much it's stretched out. That's what that x is equal to. So we can do that. So it's just going to be 0.3 kilograms times 9.81 meters per second squared. And then our spring constant, which was given in the question, is 43 newtons per meter. So we go 0.3 times 9.81 divided by 43. And it looks like 0.0684, or a nicer way of saying that would be if we move it over 2 spots, it would be 6.84 centimeters would be a good way of putting that. Okay, and I guess we only have 2 sig digs, so 6.8 centimeters would be a good way of answering that. Okay. Determine the elastic potential energy stored in the spring, having a spring constant of 150 newtons per meter. So now they're asking for energy. So we're not going to use that same formula. We're going to use our spring potential energy formula. We're going to use EPS equals 1/2 kx squared, right? Because it's asking for energy. So we go 1/2 times our spring constant, which is 150 newtons per meter, and x is 9 centimeters, so that's how much it's compressed, so it's 9 centimeters, so 0.09 meters, and we have to square it. So our spring potential energy stored in that spring would be 0.2 sig dig, so 0.61 joules would be how much energy stored in there. Okay. Okay, so here's a graphing question here. So I'm going to do this graphing question with you. So what we're going to do is we're going to do an F versus X graphing question. And yeah, we're going to graph it out. So they're always going to be force versus distance graphs. We're going to put force here. We're going to put X down here, like that. And if we look at our scale here, so we go from about 1.4 to about 2.4. We don't use a compression line because we're finding the area of the graph, and you never want to use a compression line when finding the area of the graph. So if we just go 0.51, 1.52, 2.5, yeah, if we just go up by 0.5s, then we'll get everything on there. Okay, so let's go 0.5, oops, let's go 0.5. Sorry, having technical difficulties. So 0.51, 1.52, and then 2.5. Okay, and then on the X, these are really ugly numbers to work with. So what we can do is we can take these and we can move the decimal place over 2 spots. Like that. So instead of 1.1, we can say 1.1 times 10 to the negative 2, right? Which is the same thing there. This is 1.3 times 10 to the negative 2. So now we're going from 1.1 to 2, which is super easy to figure out. So 0.51, 1.52. So when we label the units, we don't want to just call them meters. They're all times 10 to the negative 2 meters. So we put in there. And these are newtons up here. So we're ready to graph. So we have 1.1 and 0.47 to 1.314. So that's going to go there. And then we have 1.3 and 1.66. Let's go there. And then 1.5 and 1.86 and 1.6 and 2.06, 1.8, 2.25. I feel like I'm doing an ASMR video. Okay, 1, 1, 1, 1, 1, and 2.25. And then 2 and 2.45. There we go. Okay, it's going to be really hard for me to draw a line of best fit, so like that. Let's make those shark fins in there. So that's my line of best fit. If I was on paper, I'd do a way better line of best fit, but that's what we have to work with. So that's what we're going to work with. So we're going to figure out the spring constant and the energy stored in the spring. So like we said before, our spring constant is just our slope. So I'm going to pick 2 points. I'll pick this as point number 1, and I'll pick this as point number 2. It's a horrible line of best fit, so we'll just work with what we have, and then we'll find our slope here. Okay, I'll have to go in between the two. So slope is going to be equal to y2 minus y1 over x2 minus x1. So if I go and I take a look at our y2 and our y1, we have 2.2 and 0.5. And then our x is 1.7 and 0. Okay, so this is a mistake that a lot of people make. So what a lot of people do is they'll just put 1.7 and 0. But that's not what they are. They're not 1.7 and 0. They're 1.7. And if we take a look at our units, oops, wrong one. Sorry. Where am I? Yeah. Ooh, that's my other video that I'm making. The units are times 10 to the negative 2 meters, right? So we have to put those units on there because it's not 1.1, it's 1.1 times 10 to the negative 2. So yeah, if we switch back to this and we put on the times 10 to the negative 2 meters minus times 10 to the negative 2 meters, we get the correct answer. If we didn't put that on, we'd be super far off. So 2.2 minus 0.5 divided by 1.7 times 10 to the negative 2. And we get our slope, which is our spring constant, to be 100 newtons per meter-ish. And like I said, that was a really bad line of best fit, so we'll work with what we have. Okay, and then if we want to find the energy stored in the spring, that's like the work, that's the spring potential energy. What we can do is we can find the area under that graph. So we'll have to break it up into 2 different parts. We'll break it up into this rectangle and then this triangle up here. Okay, so those are the 2 parts that we're going to break it up. So to find the area of this rectangle, we would just go length times width. So length times width. So for 1, it's just going to be length times width, and then my length is 0.5 newtons, and then my width is 2. right? But it's not 2, it's 2 times 10 to the negative 2 meters. So we have to always put those units on there to get the correct answer. So we get 0.5 times 2 times 10 to the negative 2, and we get 0.01 joules. So that's what's stored in there. And then for our second one, it's a triangle. So it's going to be 1/2 base times height. So it's going to be 1/2. My base, let me switch back to it. My base looks like it's 2 times 10 to the negative 2. And my height, it goes up to about 2.5, but it only starts at 0.5. So my height here is going to be 2. So 2 times 10 to the negative 2 meters times my height, which is 2 newtons. And if I go 0.5 times 2 times 10 to the negative 2 times 2, I get 0.02 joules. And then I add those two numbers together and I get 0.03 joules as the energy stored in my spring. Okay, so not very much energy stored in that spring. So I have one more question for you that I'm going to do right here. So if a spring has an elastic constant of 4.5 times 10 to the 4 newtons per meter, what is the energy stored in the spring when it's compressed from its equilibrium position by a force? So they give us a spring force, and they give us a K, they give us a spring constant. So that's what we're going to use to solve this question. Okay, so what we're looking for is what is the energy stored in the spring. So we're going to need this. And I have my spring constant, but I don't have my X. So I can use my other formula. I know a spring force, and I know a spring constant. So if I move that down there, I can find X, and I can use that, and I can plug it into there. So my spring force is 1.5 times 10 to the 3 newtons. And my spring constant is 4.5 times 10 to the 4 newtons per meter. So 1.5 times 10 to the 3 divided by 4.5 times 10 to the 4. And I get 0.03 repeated meters. So now I have everything I need for this. So 1/2 times my spring constant, 4.5 times 10 to the 4 newtons per meter, all times by 0.03 repeated squared. So I'm going to square my last answer, times by 4.5 times 10 to the 4, times by 0.5, and I get 25 joules. So for that one, I needed both of these formulas to figure it out. Okay, so that is the homework, not as much homework as last time. So that's springs and that's force times distance. And let me know if you need any help. And yeah, that's it for today. Thanks.